got a little nutty on me, all right? Let's control that volume, because you kind of lost it last Friday, but it wasn't so bad, but don't let it get bad. Let me get the doors. Just a little bit of class business. Obviously, we're still off the test. I guess I should bring this up first. I got items for sale, okay, a scarf, a hat. One of you might really want these, your prescription glasses, and then I've got these and this up here. So if any of these are yours,
They're alcohol.
just come claim them. Why do you wear these? It makes everything screwed up. You really would think someone would clean their glasses. Anyway, if any of you need evidence, I own a cat. See that? Pretty good. We're playing, finger monster, and that cat just went. And then it got infected. I literally have cat scratch fever. Let's see. Now, you got a homework up, and so I have office hours again. I'll try to make them technically 12 to 1 tomorrow and Wednesday. I usually am in by 11 in case you can't make it. I may be a little bit late, but anyway, but I'll try to be there for 2 hours, 11 to 1, tomorrow, Tuesday, and Wednesday. Your present homework is not very hard, but the next one will be a bit more difficult. You're going to have those, all right, as we'll review in a minute, now you have S interior, S exterior, S total, A, and G to calculate in the gas expands and gas contracts. So write all 12 variables. So those get harder. So I'm going to throw a couple, and there will be, like one of the harder questions on test 2, like in that section before the derivation, is going to be the same thing. The gas expands and gas contracts, but it's going to be all the variables. So it's going to be harder. It's just natural. Let's see. I guess we don't have much else to say. Anybody have questions? We're okay. Question?
On Friday, you said something like delta U is equal to delta Q under certain conditions. I think you said constant V.
Constant volume, that's right, because no work is done.
The condition stated sounds like there is neither isothermal nor adiabatic. Is that correct?
Let's see, I don't know that it matters.
Okay.
Yeah, I don't think it matters.
A second question. You remarked about a question asked by another student years ago, in which I think it was dP dt is equal to nR over V. And he said, well, that's good. You can do that for isothermal, but you can't do it otherwise.
Oh, I should have said isochoric, actually, that would be constant volume.
Oh, okay.
Right, so if I said that's a mistake. Especially in that second hour, I was kind of flipping over myself, especially because I was kind of writing that off the top of my head. So yeah, I know Friday I was a little off, guys, and it's just that happened, so I hope it didn't go through too much. So no other questions. All right, let's just review what we did last time. Let me remind myself. I think we talked a little bit about the whole Boltzmann formula. If you have questions on your present homework, that will be exactly what I asked on the test. And I'm not going to broach it again, but so those questions, a night on a chessboard, it'll be on the test, but I'm not going to bring it up anymore. Because, I mean, it's easy. That should be a giveaway. Let's see, what else did we talk about? I guess the most important thing I could bring up is where am I at my notes? Sorry, I'm off my notes. I never expressed these guys this way. Now, this guy should get a star, but now you know how to Legendre transform the other changes. Minus PdV plus TdS. Sorry, TdS. I'm doing off the top of my head. I'm making mistakes, but I did get it right. Okay, then I transform away the volume dependence and I put it on pressure. It also changes sign. I remember H is the one that's all positive. Changing A. This was the one that's all negative because it still has its volume dependence, but I transform away the entropy dependence. And then Vg is a mixed one. It's VdP minus SdT. And so, all right, you have this one, and again, this is heat, and actually, I shouldn't have a star. You already have a star by the change in U is the change in heat and the change in work. So you actually, I should not do this, right? You should be able to derive this from heat plus work, all right? Remember, try not to memorize all. Don't try to memorize this. Just do, when I was doing this, although I flubbed almost there for a second, I'm just doing little Legendre transforms in my head. It's not that, yeah, I'm a professor at this, but if you can't do it in your head, you can easily write it down. So you saw how I do that. Now, from these things, I do derivations. Like you saw last time, I did derivations on adiabatic reversible, dP, dt, dB, dt, and I'll have you do one on the homework. And I don't know how they'll appear on a test. They may not. I don't know. I haven't written the test yet, but it is legitimate material. And those were difficult. I don't know that I'd have you derive those unless I really gave you a good head start. Because as some of you have asked, like, well, how do I know how to begin? Well, I don't want you just floundering, so I'll tell you how to begin if I ask the question. Which again, the test is a ways from now, so I'm not really thinking about it. Okay, then we started doing some derivations. So just to remind you, we can start out with, especially these two guys. I did a lot of derivations with entropy, just because I've done a lot of other type of derivations. And we did this one, just to remind you don't have to write this down, you already wrote it down. Starting with changes in U, I can divide by the change in V. Is that right? Yeah. So that was one that we did. And we did the change in S, oh, my handwriting's bad today. We did this one, and that was minus NR over P, which kind of makes sense. You know, whenever I see a derivation, I'm not promising this is always the case, but whenever I seem to write something with volume versus pressure, like the same thing except I change volume with pressure, I always notice that V's turn to P's and I pick up a negative sign. It just seems to generally happen that way, so if I ask that, that might be something to look out for. A little bit of a hint. And I don't think I have too much to say about this. One last class business. That camera, I think, is almost out of juice. So it said it only had 45 minutes of power, so I may, if it run out of power, I'll end class early. So if you could, it'll make a little beep sound when it craps out. So, okay, now I managed to waste most of the class on reviewing new material. Okay, I'm going to start here. With changing, I'm just writing it down again, PDS, I'm writing it slightly different. And I want to remind you, as I do constantly, the change in a function, two variables, is always the x at constant y, plus the change in f with respect to y at constant x, dy. Okay, just to remind you, God knows we've done that to death, and then therefore, I'm going to do a little derivation. I'm going to keep going down here, just heads up. Du, ds would be t, and du, dt would be minus p. Okay, that says, hopefully Charles' way, that's mathematically kindergarten level. Okay, now, funny enough, again, I'm going to work off to the side, and I'm going to come back here. So I have a little bit of a border here. Remember this. Euler's criteria. Remember, I brought it up so long ago. I don't know if this is really good for me to do this. You may have noticed I've done it a lot. I did it recently with the Clausius inequality. I bring up something and I drop it for a couple of months, and then I bring it back up. And remember that Euler's criteria was for the exactness of a change of a function. So I have a change in a function. Is that derivative, is that exact? It's not a derivative, anyway, is the point. And I've done exact and exact a zillion times. And that is, oh God, where am I on my notes? Sorry, I am lost. Here we are. And that is that it was the order of double differentiation is irrelevant. And now, again, we have to have this kind of funky, this matters a lot. Okay, the change with respect to y at constant x, and whatever that result is, which is going to be this and this, then the change with respect to the other guy at constant y. And then that's equal to the permutation. Now again, this part that we like to forget actually doesn't matter. Okay, just doing the same thing, and I'm inverting it. And I'm still not going to forget what's held constant. Again, it matters a hell of a lot. Okay, Euler's criterion, we've seen it before. And we used it. Oh yeah, we actually used it. So I showed it to you, then we used it for heat and then heat over temperature. Remember that? So anyway, we've done this a lot. Okay, now let's go back to here. Now, Okay, here is here, and I just have to recognize that F. Now again, if I ask this on a test, and I usually do, and you are just floundering, just go slow and do this, right? X is S, Y is V. And I've identified these parts as well. Oh yeah, right here. What am I doing? It's right here, all right? So now what I have is Euler's criteria. Okay, again, I've asked you to apply this for this. You're floundering, you're panicking, so you write this down and you just fill in the blanks. It couldn't be easier. X is S. The change in U with respect to V, which is this. That's going to be a constant S, and this is a constant V. It's equal to the change in Y, again, is V. Change in U, sorry, I almost wrote F. Change in U with respect to S, and constant V, and constant S. And last bit, I've already identified this. Why is the change in P with respect to S and constant V, oh God, please tell me I'm doing this right, yeah, is equal to the change in the UDS. Oh, I'm sorry, I shouldn't put the constants there. Anyway, I won't fix it now, it's too late. It's too late. Okay, there you go. And we solved this last time. It is minus P over CV. We did this in that second hour. And I think I may, I'm not leaning toward actually having you derive this on the test, because I think it is a little too difficult, but I'll find a way to use them somehow. That way it's not just a giant waste of your time. Okay, and this is called a Maxwell relation. Wow, my handwriting suddenly got better. So, the cat scratch fever is going away. So what Maxwell relationships are useful for is often, well, we're going to write, obviously there's four of them, right? There's four energy functions. I'm going to write them all down. I just want to be very careful in the derivation. If I ask you to derive it, I want to see this. All right, so that's kind of important. I want to see all this. I want to see that you know where it came from. And just write it all out. Besides, it's easy, right? If I ask this question, it's easy. That's a giveaway. Those are points given away. What's important is, when I do A and G, is that there's some things like this. Okay, let's look at this one. Okay, now last time I solved this guy. I solved this one, and it wasn't too terrible. That was the second or third one I did. No, this was the first one I did. Remember, this was actually kind of easy. The others were a little bit harder. Now this guy, I had no idea what to do. You see, I know that S, the problem is S is KLM number of microstates. And then taking its derivative as a function of pressure, that means I have to know how the number of microstates change with pressure. I barely have a grasp of what a microstate is. That sounds it can be enormously difficult. It's what you do in physical chemistry 6. Technically, that's your last year, that's your last semester of classes in grad school done by your second year. So in physical chemistry 6, statistical thermodynamics, you do learn how to do these calculations, but right now, I'm stuck. This is way too hard. But notice that I transformed it to this that was still a little bit iffy, but I did get an answer. So in other words, something I have no clue, now I have a clue, all right? And I can look these things up, right? This is easy. So that's what Maxwell relationships do. They get you from sticky situations to answers. So let's do the others. And I'm going to show you a trick. I don't like tricks, and I swear to God, one time a student ever yelled at me was when the guy simply wrote down a Maxwell relationship. When I asked for the whole derivation, he just wrote the answer. You write the answer, no credit. I don't know where you got that. All right, let's do the others. And here's the trick. BDP plus TDS. Okay, as opposed to write all this down, you know I hate tricks, I hate tricks, I hate tricks, I hate tricks. But this one is too good to not show you. There's a pattern. Let me just write down, let me write it down. Notice I'm not even thinking about it because I'm looking at the trick. Oh, sorry, that looks awful. OCD. Okay, how did I just knock that out? Okay, d blah at constant blah. Here, let me write that. Here, sound like Cartman. There. dV, ds, at constant p, is dt is t dp at constant s. There, there. Yeah, okay, I did it right. Let me double check that I did it right. TDP at constant s. dps at constant t. Again, how did microstates change with volume? It would help if I had flipped this over. Remember that you can do this. This might come up. This is often a trick that I'll throw into a question. Remember, this is A over B, so I'm just saying B over A. Maybe it's a little bit easier to see. Again, remember that entropy, the function of entropy is K ln number of microstates. The number of microstates may be a function of volume, but it may be also very complicated. And so this derivation may be very difficult. This guy, we actually did not do this one last Friday, but it may not surprise you. Again, when I change pressure and volume, instead of a CV, instead of a P over CV, I'm going to have a CP over a V. So I see pressure, and is that right? Yeah, I just did the derivation just a few minutes ago. It's actually relatively easy. So I may have you do that. I'll have you do this guy on the homework. It was very, very easy, so don't worry about it. Notice that I changed these for P's, I flipped it, and I picked up a minus sign. Again, when you see pressures and volumes being switched out, this tends to happen. So anyway, maybe that'll help you on your homework. Okay, so Maxwell relationship, same Maxwell relationship with A. A is the one that's all negative, which is a function of temperature and volume. Yeah, you can see, you get to tell me. Okay, first thing that goes here. Pick a letter. S, but you just lost a point. Why? Right, there you go, minus. Don't forget the minus. Okay, down here.
V.
Right. Blah, blah, at constant.
T.
Right. T. White.
P. Minus P.
There you go.
G.
At constant.
V.
Blah, blah, blah. So forget the minus signs. They just canceled out. Just make them plus. I don't like to avoid them. And remember, these can be inverted. Let's do G. VDP minus SVT. And I'm just going to write it down. P at constant T. Okay, let me make sure I got that right. Yeah, no, there was anything I didn't get it right. Okay, now when we do, so what's a little bit more useful about A and G is that here again I see, you're going to run into, when we do all these derivations that I've been warning you about, not to scare you, but they are coming in the next one, working on the test. Derivations like dHdP at constant T, the last question on your test one, you're going to have a lot more of those coming up, except they're going to be harder, and you're going to run into this. You run into this, and now you're stuck again. S is KLMW, number of microstates, and there's no solving this. Why is this good? This one's very easy to solve. And of course, I'm telling you to solve this for a perfect gas. And what is this? Oh, come on, you should be able to do it in your head.
Zero.
Perfect. NR over V. NR over V. Right. P is nRT over V. NR over V. Changing T. Okay. Something you can't solve is something you can. Same deal here. You run into a derivation, but you have an easy solution. NR over P. That's right. NR over P. That's very easy. What the hell's wrong with you? NR over V. Just to remind you, okay, so these two pieces are very, very, very easy. And especially, again, they're very good when it comes to changes in entropy. Sorry, that's awfully messy. Not a good word day. Okay, example problem. Here's an example problem. This would make a good extra credit question. These are questions, this is class of questions that people came up with a long time ago that every physical chemist eventually runs into. And so let me throw one at you, and then I'll give you a handout with a couple more examples. Again, getting really loose and fluid. Training for a boxing match, right? Getting loose and fluid so that you can handle these derivations. And one is, in particular, is to take these changes in entropy, which again are nightmares to actually calculate, instead of finding clever ways to figure out what they are without having to do bloody statistical thermodynamics. Okay, what you want to do, all right, so now your job is to do this. Again, I don't even want to try this. It sounds horrible. And it turns out there's certain measurements you can make. I avoided it. I just noticed it there. Anyway. Okay. So when it comes to materials, there's a lot of physical constants that engineers can measure. It did measure a long time ago, like 100 years. And one is called alpha. Is how volume changes with temperature and constant pressure. And this is referred to as the isobaric thermal expansive, how big it gets. I can't pronounce it. Expansivity. The isobaric thermal expansivity. I have a hard time with that. Now here's a funny thing. If I heat the ocean 1 degree, which we did in the last 50 years, if I heat the ocean 1 degree, does it expand more than when I heat a cup of water 1 degree? Total displacement, which is bigger? The ocean or a cup of water for the same temperature change? Come on, this is sensible. The ocean. I mean, they both expand maybe like 1/10 of a millionth of a percent, but you're starting from a much larger number. So of course the ocean expands more than the cup of water, making this useless unless you do this. Now it's generalizable. Now you can report this in a handbook of physical constants. Guys, well. so now this is useful. Also, there's this guy, kappa. So I'm trying to draw that right. This is the isothermal compressibility. That's a little bit easier on the tongue. Isothermal, and if I'm going to compress something, I'm obviously going to add pressure. Now, same deal. For the same reason, you want to be able to put this in a table of numbers and explain all things, but it matters your starting point, so you divide out the starting point. Okay, now dV/dP, positive or negative? Again, practice. You know I'm going to ask this on the test. dV/dP, is it positive or negative? Pressure goes up, volume goes down, positive or negative? Right. Positive or negative. All right. People don't like to print tables of number where a minus sign appears constantly. They just don't like that. So it was given a minus sign. So that the tables of numbers in all the books, all the engineering books, all the engineering handbooks and tables, they didn't have to add a negative sign by all the numbers. That just got rid of it. Ink was precious. You know, they used to make it out of cassewood. No, I'm just kidding. They didn't do that. But people don't like to read it. All right, so the trick is get this, which is unknowable in terms of these things, which are easily measured, especially for gases. So these are, you know, we do this with P equals nRT, right? And so easy, a little bit harder for liquids and solids, but it can be done. It has been done because you need to know these things when you're building a skyscraper and whatnot. Okay, now the trick is that this is useless. I don't see, you know, when you're measuring how much something expands, entropy isn't going to be part of it. It is, actually. It is, because I can relate this to this and that. It is there, but it's just not going to jump out at me. I can't change the entropy. I don't have the entropy regulator. I don't have an entropy hot plate. Although heating does change entropy, I just don't know how. So what I want to do is I want to get rid of this, and I want to change it in terms of, I need to get something with B's and P's and T's in it. Okay, now here's a trick. It almost always works. Now in terms of homework, what I'll give you is when you have a terrible derivation and you need to use a Maxwell relationship, and we're going to work examples. God knows you're going to do it on your homework and on the test. I probably will give you, oh, by the way, you might need to know these Maxwell relationships. On homeworks, maybe I won't. I'll make you struggle a little bit more on homeworks than I will on tests. You're better off that way. Okay, here's the trick. I've got 4 possible equations. So if you don't memorize these Maxwell equations, do not do that. You can't. It's too much. You've already hit too many equations. You can't memorize them all. So how do you know which one to go for? It's usually a function of these of the guys on the bottom. The correct Maxwell equation will be found with an energy function that's a function of volume and temperature, whatever's at the bottom. That would be Helmholtz, that's A, right? A is a function of V and T. All right, so again, without trying to memorize it, okay, all right, I've been doing this a long time, so I do know the change in A. That's the one that's all negative. So I don't, the Maxwell relation will be positive. And therefore, dP, dS, I know I have it written, it's right up there, but I'm just doing it again for the hell of it. dP, dV.
You have SDT up there and then TDS down there.
TDS.
Huh?
It's SDT up there.
Okay, I'm stupid. All right, dP dt, constant V, ds dV, constant T. Okay, that is right, because that's the one I'm looking for. All right, this is clearly wrong. Look, if this was a test, I would have figured out my mistake. It's a little harder when you're in the public eye, all right? But anyway, okay, what's good is I've got something that's useless to something that is. I've now got my P's and T's and V's. But now I got to express it in terms of these things. That is a little bit of a pain. So the trick is Euler relationship. Right, so what I need to break this up into smaller pieces. In the Euler relationship, x, and again, don't memorize this. It'll be, if you need it, it's on the cheat sheet, or part of the question. There is a pattern, x, y, z, x, z, x, y. So you may notice that there's a pattern. And -1 because life is kind of difficult. Okay, again, you're at the test, you're freaking out. I've given you this much. All right, I've told you this. You figured that out, which wasn't too hard, or maybe it's in the back of maybe it's in the cheat sheet. And now you just got to figure out x is P, y is T, and z is I could use a little cross there so you don't think it's a 2. Okay, so now I can fill this in, and what you're going to get is dP, dt, constant V. Well, let me remind you. So this is what you want to put on the test. I'll say this, so that I follow what you're doing. Maybe I can figure out what you're doing without you being so explicit, but you're making it harder for me. And this is going to be, I can do it in my head. I'm going to bring these two over here and flip them. There's the minus sign. So I have dz, dy at constant x, dx, dz at constant y. On the other side, because I flipped them. And I haven't had the answer, so I'm just going to work with that. D, d. Okay, there you go. Now, instantly, this one is right there. So the ddt is alpha. Not quite. Alpha times v. Don't forget the minus sign. Okay, trick here. dP, dv, but I've got a dv, dp. Okay, I'll divide. Okay, so what's dv, dp?
It's negative V2.
Negative d kappa, right? Don't forget that. Alpha over kappa. There we go. All right, again, just me working problems that I'm going to ask. I don't do enough of that. Well, I try to do a lot in the next hour, but anyway, so again, this is the kind of thing I'll throw at you on homeworks and tests. And we're going to spend a good week or two on this, so hopefully you'll kind of get used to it. Well, I don't have much else to say other than, of course, I will be throwing example problems at you, and I'm going to work you so hard on these. I know it kind of sucks, but then remember, when you walk into that test, you legitimately, honestly, you tried this, and when you can't answer a question and you're stuck, and you really tried, you work with your friends, your study group, and then you get the answer. Don't let your homework be bad if you don't have to. And it is actually, it is good. It's good for you to figure out how to do questions, to try them on yourself. But when you just can't, then you go to a study group, you get some help, or come to office hours, because that's what I'm there for, and that will free your mind. Now, if you start out with your study group, you're screwing yourself completely. You're setting yourself backward, not forward. So I learned that from a chemical educator. Okay, we're about to really switch gears. We're going to go on to delta G and some other stupid crap I don't care about. We're pretty close to a gas expands, a gas contracts. Give me delta G, A, S, T. We're actually almost done with that. This next homework, we'll have that, and then it's over. And then as we get, I'm going to start talking about delta G's now. And once I do that, we're going to then launch pad into actual chemical reactions, and it becomes much more realistic. It does get a little bit more difficult, but again, we'll work lots of example problems so that it's not hard. So all of this came from Josiah Gibbs, and oh, what a wonderful name, Herman Helmholtz. Actually, I don't know much about Herman Helmholtz, but I do know some things about Josiah Gibbs. So actually, a lot of this, in terms of basic thermo, what is there internal energy, is there enthalpy? That was Joule and Lord Kelvin, Thomson, same guy. They figured out a lot of that basic stuff out, but when it came to the harder stuff, like actually applying it to chemical reactions, because they were doing gas in the box, right? These guys started figuring out how to calculate whether things were spontaneous for just about anything you can think of, real things. That other stuff, gas expansion, gas contracts, it's not that terribly important. Okay, so I don't know much about Herman Helmholtz, but Josiah Gibbs, can anyone say 1800s? He was about the most boring man that ever lived. He was at Princeton, and he did a lot of derivations, and then he dug a grave and jumped in it. That's as exciting as he got. His father was awesome. He was like an 18th century rock star. He's actually a lawyer, so screw this guy, but his dad was cool. His dad was on the Amistad trial. Has anyone, have you seen the Amistad, that movie? It came out when I was in college, and that was 5 years ago. Gee, thanks. Okay, about 20-year-olds. It has Matthew McConaughey. Oh, come on, you gotta love him. Anyway, it has Matthew McConaughey. None of you, seriously, none of you ever saw this? None of you? Down. What's that?
It's like the slave trial, right, or something like that?
Yeah, let me tell you what happened. So, Josiah Gibbs' father is in the movie. It's worth downloading, it's pretty old, they don't care if you download old movies, and it was really, really good. So what happened was, the ship, the Amistad, shows up in Puerto Rico with a whole bunch of slaves. And the United States, no, that was illegal. They had just made it illegal to import people, kidnap them from Africa. Imagine that. Well, we were really forward thinking back in the 1800s. So this was illegal. So the ship shows up, and all the people there are like, buddies, what the hell do you think you're doing? We know where these guys are from. They're like, no, they're not. We just found them in the ocean. Right, that was believable. So Puerto Rico says, no, you need to get out of here. This is illegal. We're not having anything to do with this. In the meantime, the slaves, who didn't exactly care for their situation, they managed to escape. And these guys were smart. Now, they didn't know where the hell they were, and they didn't know how the ship worked, but they were pretty damn smart. Now, awful things happened to them, so they killed everyone on board, except the captain and navigator, the two guys they needed the most. See, they knew what they were doing, and they said, you take us home, which the captain and navigator managed to communicate enough to say, okay, we agree. But they didn't. Now, again, they really weren't familiar with ships. They didn't know how to navigate. These guys were just stolen, they were kidnapped off Africa, so they didn't know how this stuff worked. The captain and navigator took them to New York. Managed to get off the ship and said, hey, those guys are crazy. They kidnapped the ship, put them to death. And all the people in New York said, oh, bullshit, we know what you're doing. And so they figured it out too, but they couldn't prove it. because they couldn't communicate. They needed them to tell them that they were living free and wherever they were from, and that these guys came and put them in chains. They needed that. They needed them to tell them, but they couldn't speak. His father starts hanging out with these guys, and mathematics is the universal language. He learns to count in their language. So he was trying to learn their language, but their trial is coming up. There's not enough time. So he learns to count 1 to 10. What does he do? This is in New York City. The busiest port, the port of New York is not used anymore. They actually go to New Jersey, but at the time it was the busiest port probably like in the world. This guy stands up on a pier, and he counts from 1 to 10 in this language, just screaming his head off, 1 to 10. The hell is he, a madman? This guy walks up to him. He was a Navy guy. He was a former slave, but free. Guess where he was from? The same place as those people. He goes up to him and says, "Why the hell are you counting from 1 to 10 in my native language?" He found a translator. That's what he was doing. They were able to translate what had happened to them, and they were free. And those other guys sent to prison. Sad note. They tried to take him home. They never found their home. Africa's kind of big. So they let him off, they picked a place, they let him off, no one ever knows what happened to him. Probably nothing good, to be perfectly honest. They were not at their home. So, okay, sorry for the tearjerker, but that's what happened. Again, it's one of the best movies I've ever seen. That's The Amistad. Matthew McConaughey, come on. So, anyway, that's who he was. I did want to tell you about, these guys are kind of interesting. When I get to Jermaine Hess, he was a circus clown. He was actually very funny. So, okay, I wasted a lot of time, but sometimes knowing the stuff is kind of important. And actually, I don't read regular books. I don't read history books because I'm that weird. Okay, now why is there a minus? Sorry, I don't know why I had a minus in there. I'm an idiot. As we get into actual chemical reactions, because G is a function of temperature and pressure, and we hold these constant when we do reactions because we're not idiots, G ends up being most important. So let's go over some aspects of G. This gets a little bit funky. Now again, using my definition of functions, I know this. Okay, this again is child's play at this point. Okay, so what this means is, now again, we're transitioning away from gas in a box. We're going to start talking chemical reactions. Everything will be cast in the form of changes of G, because that's the most practical. It doesn't have to be that way, but we're going to make it that way because, again, it's practical. Oh, here, just so you don't get it confused, because they're connected. So if I increase temperature, it gives energy if something goes up or down. Okay, remember, is it positive, is it negative? Like pressure, entropy is never negative. Entropy, volume, pressure, never negative. There's no such thing. Changes in entropy can be negative, but this is not a change in entropy, it's entropy. So if I increase temperature, gives energy, goes down, right. And if I increase pressure, gives energy, goes up. Now here's the thing you got to be careful about. So therefore, let me try to interpret this incorrectly, and you're going to tell me where I'm wrong. Should I always heat a reaction? Remember, gives energy going down is always good. That means a reaction occurs. Why am I doing the reaction if I don't want products, right? So therefore, I should heat every reaction because gives energy goes down.
No,
Why not?
because pressure is also dependent on temperature.
No, I have a pressure release valve on the container. It's in solution. I'm just talking about 10 degrees versus 50 degrees. Pressure's not a worry. Besides, it's an open beaker. The atmospheric pressure didn't change. All right, no more gas in a box. We're going to do reactions in solution in the cup. Okay, so you have an answer.
The reaction won't happen because you have all the energy, but that reaction won't want to go downward or want to go upward.
Well, now if you remember, if delta G is negative, then that's a reaction that's spontaneous. It goes forward. But maybe it doesn't go to completion. That's what you're going to be calculating here shortly, whether reactions go to completion or not. It doesn't. Your boss is screaming at you. What do you want it to? It sounds like you should heat up everything, right? Because gives energy goes down. Is that a correct interpretation? Yeah. Okay, one of you is cluing in. Delta G. This is not delta G. I know there's a change. This is how the gives energy of substance. Let's do this. Now, when it comes to reactions, we're going to try to figure out how to make reactions work. Now, what's happened, what this thing says is, and pressure, forget about it, doesn't matter, is we often manipulate temperature. what it says is that the Gibbs energy of A, B, C, and D, they all go down, every one of them. But what matters is products minus reactants, right, from freshmen? So if these guys' Gibbs energy go down faster than these guys, good or bad?
Good.
Good, right. A smaller minus a bigger number is a bigger negative number, which is good. We want it to be negative, right? And vice versa. If these things don't shed much Gibbs energy, but these do, don't heat it up, do the opposite, cool it. So just again, so you don't misinterpret this, because it's kind of easy to do. In fact, I used to do it when I was your age. So there's another aspect of this. So that's one way to just remember that you have products minus reactants, and this is talking about all of them at once. And, oh God, what else did I want to say? Okay, so now you're in charge of this reaction. This is at your chemical plant, and you're not getting enough products. Boss is screaming at you, right? So now the thing is, I said that Gibbs energy is important at constant temperature, but it looks like I'm changing temperature. So am I screwing this up? Remember, Gibbs energy, I need to hold temperature constant. Now, you didn't make a lot of products, and now you got to change the temperature. But now does Gibbs energy not work now? Then all of a sudden, hold on, you're changing temperature. Now you can't use G anymore. G has to have constant temperature. And then it's total entropy, and then the total entropy has to rise, right? Remember all that? Okay, the secret here is, let me get it to you because I'm going a little too slow. The secret here is that you have a reaction, you're going to do it at constant temperature. Let's say you do it at 50 degrees. What this tells you is, if these guys drop faster than these in terms of G content, then yeah, you want to heat it up. That means that the next time you run the reaction, instead of 50 degrees, you do it at a constant 100 degrees. Right, so it tells you which way to go, but once you've decided, well, I need to heat it up, which is almost always true, by the way, practically, you'll do the reaction again, you'll just do it at a constant higher temperature. So it's valid to talk about how Gibbs energy changes with temperature when temperature is actually held constant. So, a little roundabout thinking. It's not that hard, right? So anyway, that's how you want to interpret these things. It does get a little bit hairy. One last derivation, one more derivation. Okay, so is that very useful? Not quite, because entropy is kind of a pain. So let's get rid of the entropy and figure out practically how do you actually know whether C and D lead Gibbs energy with heat, which is good, or maybe the opposite. So you have to actually figure it out. And right now, that's not really helpful. I don't know that I'm going to do it with that. Okay, now again, we'll remind you, G is U with the volume dependence and temperature dependence, volume and entropy dependence removed, leaving us with this. And therefore, G over T is H over T minus S. Therefore, minus G over T. I'm actually doing a Clausius inequality. Okay, I've actually just shown you that minus G over T is the system entropy. Gibbs energy is relevant, meaning I'm doing this at constant pressure. That makes this heat over temperature is the out minus the heat over the temperature is the change in outside entropy. Inside plus outside, better T greater than 0. Just a reminder, this isn't part of the derivation, just want to remind you of this stuff. Constant reminders are good. And this means that the reaction is spontaneous. Whoops, I